Hello and welcome again to CET3116 Digital Technology. This video we're going to review combinational circuits, specifically minimization of combinational circuits, at least an introduction. So far we have learned a bit of combinational circuits. Before we enter into that, just to remind you that we classify our digital circuits into two different currents, at least for this class. One is the combinational logic circuits, in which we don't have any memory or storage capabilities, and the changes in the input determines the output. Okay, so once you change anything in the input, the output would follow. And then we want to be looking sequential logic, the last part of the course, and pretty much this is related with memory involved in the circuits, right? So far we have seen equations and properties of Boolean algebra. However, we haven't seen any association with the real life, or at least not in a specific way. So let's start showing what can we do with combinational circuits and with digital circuits. This example, by the way, is going to be very useful, and we want to be using a software for a project in which we're going to be designing a burglar alarm. So our burglar alarm basically is a device that will determine if you have a house with windows and doors, whether you have sensors in the windows and the doors, and the door opens or the windows open when you don't want that to happen, or say someone else is breaking in, and then you want the alarm to go off. So the idea is that we need to design a digital burglar alarm that fires the alarm when either the door or the windows are forced open. And suppose, as I said, the windows and the door. In this case, we're talking about specifically one window and one door. Okay, and we set the logic in this case in such a way that it will be a 1, right, if there is something going on. In other words, a 1 if the window or the door is open. If nothing is happening or they remain closed, well, the value is going to be 0. Okay, so simply you need to state that as a logic. You may think, well, I would rather have a 1 if the windows and the doors are closed, and 0 when they're open. That's exactly the same, right? Well, the idea then is that the burglar alarm was going to be set to work. So somehow I activate the alarm. I need to have the possibility of setting and unsetting the alarm. And we have supposedly a keypad in which we simply set the alarm through a key or just a switch, etc. Same thing, if the alarm is going to be set, then we have a 1. It's a signal that tells that the alarm is set. If the alarm is not set, the windows and the door disturbances are not processed by the burglar alarm. In other words, I mean, you remember, if you don't set the alarm, then anyone can break in and then you won't even notice. Well, let's see a diagram. This is the door in which you have someone entering, but the alarm went off, so the breaker leaves, or the same thing through the door, the windows. So we want to have a device, that's the one I'm going to be designing, that either with the door open on the window open will activate the alarm, or I'm sorry, or will make the alarm go off. The alarm has to be active for that to happen. Okay, or armed. We want to be looking into the alarm through a word armed. So we have the door, and then we have the window, and um, if any one of these two are one, when this is activated, we expect to have the uh, alarm going on. Okay. Now, so that's pretty straightforward. So probably you already have an idea on what's going on. Now we need to move this from that idea, that diagram, into something more logic, so that we can synthesize the circuit. So we need to describe first the model. Okay? How do we describe the model? Well, remember, they're pure logic. You're going to have on one side, you will have sensors, and it's sensors tied to the window, tied to the door, and you will have another device that is as an input, that is a setting of the alarm, either 1 or 0, and then you have the output. So only 3 inputs and output. And for that, we use a truth table to describe each and every one of the events that we would like to have, so that in other words, we're going to describe the behavior of the system. Okay, so very simple. We have the alarm armed. Okay, remember it's the keypad or whatever that you set, and then if it is armed, then we have a 1. If it is not armed or unlocked, then it's 0. And then we have the sensor for the door and the window. Nothing happening, 0, and either for the door and the window. Therefore, we have our output here, it's the alarm. And it's going to set, well, 0 if nothing is going on, and 1 if the alarm is going off. It's sounding. Okay, so of course, you can see that if we don't have the alarm set, well, automatically we know that the output is going to be 0. So for every row here of the truth table in which we don't have the alarm set, we know that there's no way that the alarm can work. So because we don't have the alarm activated, as simple as that. Then we see what happens if you have the alarm activated, but you see the door and the windows are quiet. So there's nothing going on, no problem, no disturbances. So you expect that both sensors are 0. And of course, there's no problem in the alarm, so 0. Whereas if we start, for instance, in this case, the alarm is active and we have a Windows disturbance, or well, then absolutely we need to be sure that this is going to be a 1, or it's going to provoke the output to be active. Same thing if it is the door active, or the door 1, and we won't have a 1 as well. Or in the case that we have both at the same time, well, we also have a 1. So see that with this simple truth table, we describe our system. We have the set of inputs are the sensors and the alarm set, and the output, which is the alarm. And then we see how do we want that to behave. This is our idea. This is our design. So see that we can also use verbal description, right? That absolutely can take us to the truth table. So let's see how we can do that. So verbally, we can express that whatever we arrived in the truth table exactly as follows. The alarm will go off if and only if the system is set and the door is open and the windows is closed, or if the system is set and the door is closed and the window is open, or if the system is set and the door and the windows both are open. So that's exactly the content of the truth table in words. Okay? So the alarm will be 1 only in the case in which you have these conditions. For the zeros, I don't worry. Just simply the rest of the truth table for which the values are not 1, they're going to be 0. So if we use this, and then we know those words are key. And you see, there's a conjunctive saying both things needs to be true. So the system should be true, and the door open should be true, so that the alarm sounds. And the window is closed, or if the system is set and the door is closed and the window is open, or if the system is set and the door is set and the system is set and the door and the windows are open. Sorry, right? So we put that into words, and this is the alarm, which is the output. It's going to be the I need arm true. I need either, in this case, the door is closed but the window is open. Arm, the door is open and the window is closed. And arm, the door is open and the window is also open. So see, this sentence pretty much describes what we have here. Okay. Now with this, this is a description that is very close to the description of a circuit, right? So you can say, well, this is exactly using ands and ors, right? And of course, the inverted in the case of the complementing. Well, this is the case. This is the circuit. This is exactly the description that we have here, right? So the alarm is going to be 1 whenever the alarm is set and the door is closed and the window is open, and or it's armed, the door is open, the window is closed, or it's armed and both are open. Oh, this is the circuit, just exactly described in here. So a condition, in this case for the armed, you see, is present in the 3 of the ands, as you can see, of course. That's a condition that has to be met so that any of the situations make the alarm go off. So in this case, well, we have a situation which, okay, I have the door closed in this case, but the door is open in this case, the window is open in this case, and the window is closed in the other case. And in this case, both windows and door are open and the alarm is active. Okay? So, as you can see, we sort of follow 3 steps in designing in this case, we're working with a single output combinational switching circuit or digital circuit. So first of all, we need to find the function or a description of the function or the behavior, right? And after that, well, we need to extract or synthesize the simplified algebraic expression for the function. We assume that what we have here is simplified. Okay? Well, you may have a more complex type of expression that you can further simplify. Remember, simplification is very important. The simplification makes every circuit more efficient, less cost, and much more faster. Okay? And then once we have the simplified expression, well, simply we move that into a circuit. Okay, so we realize this circuit using the logics elements that we have available. We have a pretty similar example. This is the one that is in the book. in which we also have an alarm. This is also part of chapter 4. And very simple how to map from logic description into equations and then into circuits. So see, for instance, this sentence. Mary watches TV if it is Monday night and she has finished her homework. So see, if I see that my function would be the Mary watches TV is going to be active or when, if it's Monday night and has finished the homework, right? So we can, from here, you see we have f, and then we define this as the output, and then one of the conditions is a, and the other one is b. So we can use two value variables to indicate in the truth table. My f is going to be then 1 when both are 1. Okay, why? Because we have this conjunctive and here. So f is 1 if Mary watches TV, right? And in the case we said it's going to be true, it's going to be 1, otherwise it's going to be 0. That's my output. And then a is my variable. It is Monday night, and if it is Monday night, it's true. If not, it's going to be 0. And b is going to be she has finished her homework, and it is true if has finished the homework, otherwise it's going to be 0. So the fact that this guy is true, that demands that these two has to be true. Why? Because we have this conjunction. This is and. Okay, so this is easy to map into a logic and. Right? Let's see another example. It's an alarm. As I mentioned, the alarm will ring if the alarm switch is turned on, or arm, as in the first case, and the door is not closed, or it is after 6 p.m. and the window is not closed. So we have a slightly different case. We have a door and a window, but also we have a conditions that we impose that after 6 p.m. I'm closing the door, and I expect that to be closed. Therefore, that probably because the person is gonna sleep and then shut the door, the windows, and then turns the alarm, right? So here's logically what we can say. The alarm will ring if and only if. So see, this is if and only if the alarm switch is on and the door is not closed. Okay? Or both of them. It is after 6 p.m. and the window is not closed. So how do we move then this into a logic equation? Well, it's very simple. So the equation should be this. If we're calling, remember, Z is the alarm, and A, in this case, is the alarm switch is on, okay? And the door is not closed, okay? The alarm switch is on. The door is not closed, okay? B, in this case, is the door is not closed, door is open, or simply if it is after 6 and the window is not closed. You may think, well, we should have another A here, so that, of course, that doesn't have much sense not to, have the alarm armed and the switch turned on, and then having the checking for the door after 6 p.m. And you will be right. You will be absolutely right. But this is the case in the book, so I'm showing it just exactly like that. And well, the fact that we can convert this into a circuit, very easy. But we already know how to do that, right? Now, the other aspect is that we're going to be using truth tables, all right? So next, we're going to be looking into the case in which having the truth table, this step that we already have completed for the first case, well, we're going to be using that to get into the design. So for instance, let's suppose that we have a circuit, and this circuit, we want to have a 1, okay, in the output whenever the number, right, that we are reading in the input is greater or equal than 011, which is 3, and sorry, and 0 otherwise if it's less than 3. Can we do a truth table? Of course, very easy, because it's telling certain things about the function. We know that we have 3 numbers, therefore we only need 3 variables. If we are using 3 variables, then we're going to be using only 8 different rows, and these are all the rows for a 3 variables. So I have 2 columns here, one to depict when the function is true, right? In this case, the f. But also, I'm going to use the function complemented or inverted, and the fact that we're going to be using that is going to help into figure out some interesting thing. So the idea is with this, well, we need to find the circuit that implements this. All right, I'm going to stop here because we have 21 minutes of recording, and we'll be back.